Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Kirill Glinskiy. Kirill is currently pursuing his PhD under the supervision of Evgeny Khorov. He received his master's degree in applied mathematics and physics from the Moscow Institute of Physics and Technology last year. Currently, he is a researcher at the Institute for Information Transmission Problems and the High School of Economics. Today, he will tell us his recent results about channel prediction for URLLC scenarios. Kirill, the floor is yours.
Yeah, thank you, Vyacheslav. Good evening, everyone, and welcome to my talk, which I have named "Does Channel Model Matter for Ultra-Reliable Low Latency Channel Prediction?" So first, I would like to give a brief overview of what exactly URLLC is and what its place in the broader 5G and beyond scheme. So ultra-reliable low-latency communications is one of the key development directions of cellular networks and is aimed at applications such as transport systems, autonomous driving, unmanned vehicles, and industrial Internet of Things. And it imposes extremely strict quality of service requirements on both the reliability and delay. For example, the delay should be below 1 or 10 milliseconds, and the reliability is beyond 99.991%. So extremely high requirements need to be met. To achieve these requirements, 5G offers a novel technology, which is called massive MIMO, and is significant improvement over the older MIMO in 4G and previous cellular networks. So the massive MIMO technology relies on massive antenna arrays on both the transmitter and the receiver that allows us to massively increase the signal to interference and noise ratio and support much higher data rates and reliabilities. However, to fully utilize the potential of massive MIMO, the base station needs to select efficient precoders. That is, the way that the signals sent from each antenna are modified. And this precoder depends on the channel state, but the channel changes with time, and that results in the problem called precoder aging. And naturally, the precoder aging results in decrease in signal to interference noise ratio, and thus the network performance itself. The simplest solution to the precoder aging problem, that is to keep the precoder updated, is just to keep the channel state information as recent as possible. However, the channel state information is obtained by using reference signals. For example, sounding reference signals in 5G. Each reference signal transmission, though, increases sounding overhead and robs us of variable channel resources and therefore the channel capacity. By using channel prediction methods, in one way or another, we can forecast the CSI ahead, the channel state information ahead, and by not utilizing the references as far as frequent as possible, we can save the channel capacity for more useful transmissions. The channel prediction problem is quite old and well developed. Many methods were proposed over time based on statistics, signal processing approaches, geodetic methods. Recently, with the advent of machine learning methods, they have been also shown to be quite promising for this task. However, as we all know, the machine learning methods also always rely on the high quality and representative data set. And that's where another problem steps in. Channel measurements are quite hard to gather, especially for mobility scenarios and massive MIMO scenarios. The measurement equipment is extremely expensive, and for each antenna pair, can come up into thousands of dollars. So if you want a 64x4 test bed, well, that results in hundreds of thousands of dollars in costs. Additionally, we want for the set to be representative, so it has to include multiple scenarios, and each scenario has to span at least a certain time. So that means that measurement runs have to be quite long. That results in huge amounts of computations and memory to be required. Additionally, as the test bed is quite cumbersome, it requires additional measurements for it to be truly mobile, like placing it on some specific carriage or in the vehicle. Finally, a lot of time, the bandwidth, which was reserved for cellular networks, is in fact in licensed spectrum. And most of the time, the cell operators which possess the bandwidth are not eager to share it with researchers and are generally non-cooperative, which also limits the ability of scientists to measure the channels and provide and gather the representative data set. So for the most of the time, researchers have to rely on channel models to obtain the data sets, to train their models and evaluate them. However, that brings us to yet another issue, and that is the trouble of evaluating the channel models and their usability for this task. So look at this example. Here we can see two sets of black and white pictures, which were both used to train certain types of classification models. On the left is the MNIST data sets for classifying handwritten digits. On the second picture is the Kaggle computer tomography scan data set for tumor detection. In a sense, both of these pictures are similar. They're black and white pictures for classification. One could say that with some certain pre-processing, pretty much every metric, in a sense of, for example, number of black and white pixels, correlations, could be matched. But from a machine learning perspective, it's absolutely not obvious, and it's in fact really not correct that the model that shows the high accuracy on the left task would achieve the same high accuracy on the right task. Moreover, for example, if imagine yourself as head of some hospital, and some new startup reaches to you and says, "Well, we have developed this new machine learning method that can accelerate your patient study, and for that we have developed neural networks which classifies based on CT scans." And then when you ask them about the accuracy or some other metrics, they say, "Well, we couldn't really gather the data for exactly our CT scan, but we have the same task of black and white image classification." Well, of course, it would result in this novel startup being kicked out on the street, as obviously these tasks do not exactly transfer. But for the channel prediction and channel models, this difference is quite often much more subtle and not really that obvious. So as there have been many models proposed over time, and over time many papers have evaluated their algorithms on, for example, one channel model, then the second algorithm tests itself on the other model. Of course, that results the ability to compare the different algorithms one with each other and to determine which one is truly superior. So the problem, which I'm going to try to give an answer to, is, well, indeed, how do we evaluate the channel prediction algorithms in URLLC high mobility scenarios, and how does it affect the performance of modern machine learning-based channel prediction algorithms, including not only the basic accuracy, but also accuracy under such events as model decay and data drift. So I'm going to briefly give an overview of the specific subtype of channel models I'm going to talk today. That is the so-called geometry-based stochastic model, or GBSM. There are many variations of it. The most perhaps well-known is Quadriga, which implements within its features the modifications known other models like 3GPP, standard CDL model, or the Winner2 channel model. So the main concept of GBSM is to represent the environment as a set of scatterers, where each scatterer is representative of some obstacle in the environment. This obstacle can be quite big in size, and therefore multiple rays, which are sent from the transmitters and receive the receivers and represent electromagnetic waves, can scatter off the scatterer and then be received by the receiver. So generally speaking, the parameters of each ray, that is its angles, its power, its delay, and the elevation of the cluster are determined by some predetermined distribution. For example, it can be obtained using experimental measurements, or just considered to be from one of the known family of distributions, like, for example, to represent their relay channel. However, this paradigm does not strictly specify the way that the channel evolution or the channel change with time is modeled. And there are many time evolution approaches. Some of them are less complex, some of them more complex. The three most prominent I'm going to talk today are the Doppler fading, the drifting, and the cluster birth death, which all of them can be implemented and are available inside the quadriga channel model. So the simplest and quite possibly the most widely used channel model, which precedes GBSMs, is the Doppler fading model. So in this model, we preserve the scatter parameters, all of them, the powers, the delays, the angles, and instead we assign each scatter direction and velocity. So we can represent it as the environment moving, or if we coordinate all of them moving in the same direction, we can assume that it's basically the receiver moving. And for each of them, we can calculate the per scatter Doppler shift, which is proportional to the velocity of the scatter and to the frequency of the base signal. After all, we can calculate the Doppler shift, and when we sum over all the paths and all the signals, we would see the resulting Doppler fading, which is often called sum of sinusoids, as indeed each scatter introduces, each ray introduces its own sinusoids with its own frequency and its own power, and they result in a Doppler spectrum, and the Doppler fading itself occurs. The edge case, which I'm going to give a little bit attention later in the talk, is the edge case where we have only one ray per scatter, and therefore one Doppler frequency per ray. That's called the partial Doppler case, and it's the simplest of the GBSM channel evolution approaches. However, of course, multiple disadvantages can be seen to this approach. First of all, it does not consider the scatters to be either moving or moving in the sense that their parameters are updated, nor does it take into account the fact that the environment can change with time. After all, for example, imagine a car that moves in the cell and then disappears from our vision. Naturally, it does not work as a scatter anymore. So to fix those drawbacks, multiple additional channel evolution methods were proposed, which work on the scatter level and actually update its parameters. So the first one is the so-called drifting. So its name, it means that the scatter themselves drift. So the user can move in trajectory and therefore results in user drifting. So as the user moves and its trajectory is updated, the angles and the paths from the scatter to the users are updated. That means that the parameters of our channel, for example, the path loss per scatter or their delay or the angles of arrival, will also be updated. And this happens in a continuous fashion. However, the scatters themselves, their number, do not change. So, generally speaking, this method is considered to be quite useful and is in fact included in 3GPP specification as extended mobility procedure. However, it has its own drawbacks, as it does not really support extremely long simulation runs. For example, it's reasonably assumed for it to be applicable for the movements within 10 or so meters. And if you want to model larger scale scenarios, we would have to resort to the third one, the most complex channel evolution method, that is the cluster birth death, which is included in quadriga channel model. It's not exactly in the 3GPP specifications yet. And within it, we can split the trajectory into multiple segments. And from one segment to another, we can update the scatters themselves using the Burgess process, meaning that during our intersegment trajectory, the scatters from segment 1 they are gradually ramped down, and segment 2 clusters are gradually powered up. So in a way that is determined by the Burgess process, but also additional measures are taken to preserve the wide sense stationarity of the process. Of course, this typical segment length is around tens of meters, below 40 for the non-line of sight scenario, below 20 for the line of sight scenario. So 3 of those channel evolution approaches were studied in this work. And now I would like to briefly go over the channel prediction methods themselves. So a classification of channel prediction methods can be broadly split into 2 approaches. For machine learning based methods, of course, the classical machine learning, which is generally reserved for linear methods or tree-based methods, and the deep learning methods, which rely on some sort of neural network-based approach. For both of these types, we have selected a representative example, which were previously already proposed, and many papers were, in fact, testing them on various but not uniform channel prediction tasks. So the simpler one is the classical machine learning methods, which is the vector autoregressive model. It's a simple and interpretable linear model where we predict the next channel state as the linear sum of previous measurements, where the number of previous measurements is called the model order. For example, the one used in this scenario had a model order of around 30, which is sufficient to model the high velocity scenario, as it needs to be able to fit the Doppler spectrum, and is trained in a very simple and efficient manner using least squares method. And one more note to be aware of is that, as we know, the number of parameters does indeed influence the model capacity, so the way that it can fit the distribution. And this one has around hundreds of parameters as a vector model. So it has, generally speaking, less model capacity compared to neural models, but is trained extremely fast, is very fast in inference. As to predict it, you only need to apply a single linear transformation to your input data. Moreover, it has strong theoretical guarantees, is not prone to overfitting, and, well, overall, its drawbacks are greatly overshadowed by its advantages. On the other hand, we have a modern approach, which was enabled by the rising computational power, the deep learning methods based on neural network. In particular, in this case, we have chosen to use the long short-term memory neural networks, or LSTM. It's a complex model that can capture the nonlinearities in behavior and work with long sequences. However, compared to linear models, it is, of course, much more computationally heavy in both training, as it requires multiple thousand steps of gradient descent, and inference, as it has tens of thousands of parameters. Well, for them to be updated using backpropagation during the training time, and then during inference, of course, you need to pass the forward pass, which also is quite computationally heavy. Now, however, I would like to give a little bit more detail about why the long short-term memory model was chosen, and what's its standing, what are its closer counterparts in the deep learning world. So it's a modification of the recurrent neural network variant. So the recurrent neural networks are the neural networks which introduce which were introduced specifically to work with longer sequences, and they work with them by possessing a self state and hidden states and the feedback mechanism to keep the states updated. And while the vanilla recurrent neural network is already quite efficient in its time series prediction task, it suffers from the disadvantages during its training procedure, as it's trained using BPTT, backpropagation through time, which results in so-called exploding or vanishing gradient problem, and it's mainly due to the optimization, the parameter optimization, well, during the backpropagation phase. Additionally, it suffers from forgetting older events in the time series. And to solve this problem, both the exploding vanishing gradient and also the forgetting problem, the LSTM modification was proposed. The key idea is to add the so-called gates, which are additional neural network layers with sigmoid activations, to in fact modify how exactly the information does flow in the neural network, and what information to store, what information to discard during the update steps, and finally what to output during the what to output from the neural network layer. So after the LSTM layer, our channel prediction neural network has just a simple linear layer to output the channel coefficients, channel matrix coefficients for each of the TTI for the next frame to predict. And now I would like to briefly go over the simulation scenario, the scenario in which the channel models and channel predictions were evaluated. And it's a quite simple single user scenario with a massive MIMO cell, with 64 antennas, but only a single antenna non-line of sight user, which is moving in the vicinity of the cell. The sounding reference signal period was chosen to be 5 milliseconds, well, for it to be compatible with the Nyquist limit on the sampling rate and the Doppler frequency. So as a method of precoding, we used maximum ratio precoding for single user MIMO, and three scenarios in terms of velocity were chosen: 15, 30, and 60 kilometers to represent the low, medium, and high mobility scenarios. As for channel models, well, the previously described set was implemented in Quadriga and plugged into the scenario. For these channel models include partial Doppler with one ray per cluster, the 3GP compatible model with drifting, and the 3GP compatible model with drifting, and additionally the Quadriga feature of cluster birth depth. As we are evaluating the models in URLLC context, then instead of average signal to noise resonance ratio, we have chosen to instead use the 0.1 percentile. The reason for that is the following: when we are using channel prediction in a system level scenario, then it's not only working by itself, but also compounded by other link adaptation and modulation coding scheme selection algorithms. For example, OLA. A lot of them are aiming to achieve a certain level of reliability. For example, for the transmission to be reliable with 1 in a million error probability, like loss probability, and a single transmission attempt, the single transmission attempt reliability should be 1 in 1,000, which is exactly the 0.1 percentile of the signal to noise ratio. Additionally, as we aim to measure the improvements which can be obtained by using channel predictions, we have chosen to represent the gain over the baseline. The baseline is just to not predict the channel at all and use the previous measurement as a value to build the precoder. And the prediction methods are, again, as stated before, the long short-term memory network and the vector autoregressive model, which are shortened to be neural and autoregressive. A little bit about the details of the training inference pipeline. a significant problem which we were expecting to occur is the fact that the models would age during our scenarios. That is, that their parameters would not longer be applicable to the changing to the evolving channel state. Therefore, we have adopted the following training and inference phase split, where during the training phase we sample the channel with a measurement each slot, which this phase spans always for one frame. And as we are able to aggregate the data from all antenna pairs and all precoder groups, so across both frequency and antenna pairs, that means that we can obtain up to a few thousands of representative channel examples for the autoregressive or neural models just in a single frame. And during the inference phase, we use the trained model to predict the channel. And then during the next training phase, the autoregressive model is retrained from scratch, as again, it's very simple, efficient, and easy to train. And as for the LSTM network, we instead fine-tune it with the same learning rate. So the fine-tuning meaning that we preserve the original parameters of the neural network and then perform multiple update steps, not from the random initialization as in the first training phase, but rather from the initial already trained parameter set. It means that it's supposed to, first of all, reduce our improve our convergence and increase the ability to generalize. However, as we would see later, it's not exactly the case with the vanilla fine-tuning, and it still leaves much to be desired. So now I would like to go over the first batch of the results. So on the left, on the right, we can see a set of three bar plots, which each of them consists of three channel prediction algorithms. That is the autoregressive one using linear model, the neural one using LSTM. The ideal measurement perfectly knows the channels every time and represents the upper bound in our channel prediction performance. And the three columns are, in fact, the channel models used, the partial Doppler one, the simplest, the 3GPP, and finally the 3GP plus CBD, which is the most complex one to predict. And as we can see for the low mobility scenario, all three algorithms are pretty much equal in all cases. That means that, first of all, our model doesn't really, the advantages of higher capacity doesn't really show, nor doesn't really need to, as the channel changes very slowly. It's pretty much linear in its change. And therefore, all the algorithms can easily fit to this very simple task and result in less than 0.1 decibel difference from ideal in all channels. However, if we speak about the high mobility scenarios, the behavior starts to change. Well, as we can see in the partial Doppler scenario, which is both the easiest in terms of number of paths and it's stationary in terms of its clusters, we can see that in fact the neural algorithms does show some improvement over the autoregressive, probably to its higher capacity, and it probably just even overfits a little bit, resulting in its higher performance in this fixed scenario. However, for the 3GP and 3GP plus CBD scenario, we can see quite the opposite picture. The autoregressive algorithm is much more robust. Well, probably because we are talking about the very low tail of the distribution. In that sense, we have a little bit more theoretical guarantee of stability and robustness for linear model compared to the neural counterpart. However, as we can see, while both algorithms do have some improvements in 3GP and 3GP plus CBD scenario in 30 kilometers per hour, in the 60 kilometers per hour, which is the fastest scenario in our work, we can see that, in fact, in the most complex scenario, both algorithms, both autoregressive and neural ones, are, in fact, worse than no prediction at all. In fact, the difference from ideal is up to 28 decibels, and they are worse for 2 to 3 decibels than the no prediction at all. It means that the model aging is so severe that the model is actually pushing us in the wrong direction, and we are moving away from our goal of predicting the channel. And for this very quickly changing scenario, even the partial opera scenario is not perfect. We can see there is at least an 8 decibel gap in achievable signal-to-noise ratio, which means that, well, none of the algorithms are perfectly generalizable to the simple scenario. And again, a little bit improvement of neural compared to autoregressive can be attributed to its higher model capacity, which helps it in fixed scenario, but under drift, this proves to be detrimental to its performance. With those results, of course, the question arises, well, the high-based scenarios are often considered to be quite important for the URLLC, for example, for UAVs or unmanned transport. So with these sort of losses expected, how can we, in fact, solve this problem? And how can we achieve at least some gains in that regard? So the simplest approach is to, of course, reduce the model drift, reduce the model aging, and for that, just to retrain it more frequently. And that's exactly what we did. The original update frequency was 50 milliseconds. And if we raise it times 2, so that the new algorithm is built, the model parameters are updated only every 25 milliseconds. That means that we have pretty much increased our uplink overhead as the basically the number of training phases is indeed increased 2 times, but it does not contribute exactly to the 2 times decreased channel capacity. So the fact that we have significantly increased our signal-to-noise ratio, while it is partially offset with more frequent sounding, however, it will still result in a net gain. However, of course, for these very frequent update times, of course, this raises a question of can the hardware keep up with the computational requirements of keeping the models updated? And again, as we can see, the neural network with its fine-tune methodology still lags behind the autoregressive algorithm, well, probably due to worse generalization on the extreme tail of the distribution. So that brings me to the conclusion, to the results section. So the findings, which we consider to be quite surprising, is that in fact that sophisticated deep learning algorithms can be worse under model drift and under the tail scenario, where we have to predict not just the average value or the reasonable quantile, but instead which have to consider the performance at the extreme tail of the distribution. And we consider it to be because the large parameter sets is harder to adapt with the vanilla fine-tuning scheme. Well, moreover, if we talk about simple channel models, which are still often used in other papers to evaluate the novel channel prediction algorithms, these simpler channel models do in fact hide the model aging effects, which are in fact in high-embedded scenarios at least as severe as the gains itself. So it means that in high-embedded scenarios, the use of prediction algorithms can in fact reduce signal-to-noise ratio compared to no prediction in the URLLC scenario. And this discrepancy needs to be addressed. And the third one, of course, to solve the model aging problem, the naive and simple approach is to just retrain the model faster, spend more time training, but this results in the loss of uplink resources, and this trade-off needs to be considered. Finally, this brings us to the future work section. This work is not yet finished, and we see 3 promising directions to work on. The first one is to propose an adaptive parameter update algorithm, which would result in smarter parameter updates which results in less frequent compared to just retraining the model on a schedule, and would therefore conserve the uplink resource. The second one, which is conjoined with the first one, is to propose efficient parameter adaptation schemes beyond just fine-tuning and retraining. For example, some approaches like few-shot learning or meta-learning could be applicable in this regard. And the third one is, well, here we have tested the case where we have a single user with a predetermined set of with predetermined velocity, which is fixed. For this case, we can easily find the optimal parameter update frequency. However, when we have, generally speaking, in a cell, we have multiple users. For example, a single urban cell will have multiple cars, multiple pedestrians, perhaps a few stationary users, and each of them will have its own rate of model aging. And if we will use the, for example, most frequent update parameters for the car users, that means that all of the others will just waste the channel resources on unneeded updates. And that means that the scheme would need to be proposed to efficiently update the model parameters for everyone while keeping the uplink resources to be used as economically possible as possible. And that brings me to the end of my talk, and I would like to answer all of your questions, both in the chat or in the by voice.
Thank you, Kirill, for your interesting talk. Do we have any questions from the audience?
Ilya.
Thank you, Kirill, for your talk. It was very interesting. I was wondering a lot about actually the first part of your presentation when you talked about the ability to gather experimental data from measurements. So you say that there are no open source experimental measurements done by someone in the scientific area.
Well, I would say that we are very picky in terms of our datasets, so we wanted the datasets that wasn't as following. It was at least a reasonable order of MIMA. So, for example, at least 8 antennas at the base station. It was reasonable mobility, so at least I'd say at least pedestrian mobility. We wanted it, of course, it would be best if it include the vehicle mobility, and also it would need to be at least as long as to give us the quantiles we want. So if you want to measure the tail of the distribution, we have to have at least tens of seconds of measurements. And I believe that we found only one that satisfied all of our requirements. And in the end, it was not in the frequency band we wanted. It was a millimeter wave dataset. So yes, this problem is quite open, and I'd really wish that the scientific community proposed and put forward more and better data sets with time.
Okay, I see. Thank you for your intel. Also, I was wondering about the interesting results you got in the end. You revealed that using a neural net-based architecture actually shows worse performance than using something much more simpler. Can it be just because an neural net architecture should be updated? For example, some LSTMs should be reordered or something like that.
It's an interesting question indeed. In fact, it's an interesting direction. Here we have all fixed the architecture and updated only the parameters. But I can really see perhaps the notion that with time, with changing the complexity, perhaps some layers can be dropped, or something can be pruned. So perhaps it's an interesting area of direction. And I have seen a few papers on meta learning that do work with the changing the architecture of the neural network, and that would be an interesting direction to pursue. But
Okay, I see. Thank you.
One question from my side. I'm wondering where is the you showed several channel models, and you showed in your results that the more complicated the model is, the harder task for predicting. And I wonder where the real life will be. Is be like similar to the 3GPP plus cluster birth death model, or it will be much complicated, which means that it will be unsolvable task for both neural network approaches and autoregressive approaches.
Yes, an excellent question. I can't really give an exact answer for it in the massive MIMO channel prediction scenario. However, for the single user scenario, we found the real life to be marginally more complex due to the effects of how would I call it? During our preliminary work on the sequence prediction task, when we have only the seesaw and channel quality indicators, we saw some uneven time scale on the channel evolution. That means that for example, in this case, the user velocity was constant, and therefore the rate at which the channel parameters were updated was also quite constant. But in real life, of course, there is always an accelerating car moving near you, or for example, the train, the pedestrian, for example, stopped and then started moving. So there is an inherent element of randomness, which is greater in the real life datasets. However, we observed the correlation, so the algorithms that showed themselves to be efficient in terms of channel models were, generally speaking, of course, realistic channel models were, generally speaking, reasonable even in real life datasets.
Okay, thank you. Okay, so any other questions in the chat window? Okay, I guess that's all for today. Let me thank Kirill for the interesting talk. Let me also thank all the participants for discussion and participation in the seminar. Goodbye.